Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning, everyone. I'm Zainal. I'll be your host today and moderator. So I'm from the School of Chemical and Energy Engineering, Faculty of Engineering, UTM Johor Bahru. Yeah. So today we're going to have our 87th Distinguished Lecture Series under the Faculty of Engineering, UTM. So today we are very grateful and very fortunate to have the presence of our research collaborators and our longtime friends from all the way from Australia, which is Professor Jega Jegatheesan. He is a professor in water engineering from Royal Melbourne Institute of Technology, Melbourne. So maybe a little bit of a background of how we started our collaboration. Professor Jega is hosting one annual conference, which is called Challenges in Environmental Science and Engineering. So from that point, we get to know more people. So until now, Alhamdulillah, we have managed to come up with a lot of visible outputs, and tangible outputs, such as the publication of books, guest editing a number of journals. So hopefully by having a session like this, the existing MOU between UTM and RMIT, we can further strengthen the existing MOU, and as well as to have more involvement of researchers and staff from both sides. Maybe that's a little bit background about how we started get to know each other. So without further ado, I would like to invite our distinguished Dean, Professor Rafiq, to continue with the session. Over to you, bro.
Thank you, Dr. Zainal. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 87th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology, Malaysia. Today, it is my utmost pleasure to welcome Professor Jega Jegatheesan from RMIT University, Australia. A bit about our distinguished speaker today. Dr. Jega is a professor of environmental engineering and director of Water Effective Technologies and Tools, WETT, Research Center at the School of Engineering of RMIT University in Melbourne, Australia. He is also the secretary of the Stormwater Quality Improvement Device Evaluation Protocol Governance Panel of the Stormwater Australia. His expertise lies in the fields of water treatment distribution modeling, wastewater, MBR, membranes in agriculture, aquaculture, saltwater intrusion, integrated water management, resource recovery in mine tailing ponds, dye and salt from textile effluent, and novel hybrid technologies, reverse osmosis, forward osmosis, membrane distillation. He has won grants to work on integrated water management through the application of advanced wastewater treatments, research exchange with the Universidad Estuado de Maringa, advancing research cooperation through joint workshops between Australia and India, water scarcity and ways to reduce the impact, funded by the Australia-India Council grant. He is currently involved in the Climate Resilience Honiara project that focuses on designing solutions to mitigate water, sanitation, drainage, waste, and flood risks in 5 highly vulnerable settlements in Honiara, Solomon Islands. Dr. Jega is the editor-in-chief of Environmental Quality Management, a journal of Wiley Publisher, and a book series on applied environmental science and engineering for a sustainable future by Springer Publisher. He is one of the founders and the series chairman of an international conference on the challenges in environmental science and engineering, CESE, that is being held annually in several countries since 2008. Dr. Jega has more than 400 publications in the form of peer-reviewed journals and conference articles, book chapters, editorials, and commercial in-confidence reports. So that is a brief biography of our distinguished speaker. For this particular session, we will play a pre-recorded video that Prof. Jega has prepared. And after this pre-recorded video, do join the Q&A session with Prof. Jega and Dr. Zainul as the moderator. And as usual, you can post your questions in the comments section. So here now is Prof. Jega Jegatheesan from RMIT University Australia on resource recovery and concentrate management.
Good day, everybody. First of all, I would like to thank Professor Rafiq and Associate Professor Zainul for giving me an opportunity to deliver a presentation in the Distinguished Lecture Series webinar organized by the Faculty of Engineering at UTM. It's a great honor and privilege to participate in the series. I will begin my presentation with acknowledgement of country. I acknowledge the Wurundjeri people of Kulin Nations as the traditional owners of the land on which I am living. I respectfully recognize elders both past and present. Although the title of my presentation is Resource Recovery and Concentrate Management, I would like to keep my presentation mostly around water and will touch upon other resources. I hope this will entice researchers who wants to venture into resources that are important to them. I also hope the presentation will encourage researchers who are already working on resources to compare and contrast the management and recovery of different resources. Let us simply begin with the definition of natural resources. Natural resources are defined as materials or substances occurring in nature which can be exploited for economic gain. Examples are animal resources, crude oil, forest resources, precious metals, minerals, and rocks in a group, water resources, land resources, wind, power, and solar energy as another group, and natural gas. The 6 natural resources most drained by our 7 billion people are water, oil, natural gas, phosphorus, coal, and rare earth elements. We know a lot of facts about fresh water. It is only 2.5% of the total volume of the world's water. We have access to only 200,000 kilo cubic meter of fresh water. This is an important number. In another 5 years' time, 1.8 billion people will be living in countries and regions with absolute water scarcity. This is very frightening. Oil will be enough for only another few decades. Gas in proven reserves will serve for another 50 years. Phosphorus is only found in a handful of countries and will run out in 50 to 100 years. Coal is enough for nearly 200 years. There are 17 rare earth elements. They are not rare, but their exact reserves are not known. Let us recall that we have access to 200,000 kilometer cube of fresh water. 3,928 kilometer cube of fresh water is withdrawn annually for municipal, industrial, and agricultural needs. If we want to put this into perspective, the amount of water we are withdrawing annually can submerge the entire Australia by half a meter. It can submerge the entire Malaysia by 12 meters and the entire India by 1.2 meter. Also, 44% of the withdrawn water is consumed for agriculture. The rest, 2,212 kilometer cube, become wastewater. We will treat this wastewater and release to the environment to mix with fresh water. If we were able to compartmentalize freshwater reserves and treated wastewater, then every year 2,212 kilometer cube of fresh water will become treated wastewater. Thus, in 90 years, there will be no more fresh water and all the fresh water would have become impaired water to some extent. Since the compartmentalization is not possible, we do not need to wait until 90 years to impair our entire freshwater reserve. This is a scary thought. "80% of the wastewater generated worldwide is released to the environment without adequate treatment, causing degradation of surface and groundwater resources, affecting marine ecosystems, posing threats to food security. Therefore, reuse the wastewater generated from various sources is of paramount importance. In order to do so, we need to develop appropriate and advanced wastewater treatment systems. This will allow us to produce fit-for-purpose water that can assist integrated water management. Integrated water management is developed to optimize the utilization of all types of water sources, such as surface water, groundwater, rainwater, stormwater, treated wastewater, seawater, and brackish water. This is essential to meet the growing water demand in a sustainable manner. I will go through some of the important aspects of integrated water management. How could we utilize treated wastewater in a safe and economical manner? By allowing the wastewater to undergo different levels of treatment, such as primary, secondary, tertiary, and advanced treatments, we can produce different classes of water which will fit for different purposes. Generally, the level of E. coli, virus, and protozoa removed, along with other water quality parameters such as pH, BOD, COD, nutrients, and salts, will define the class of water produced. Treated wastewater is also referred to as recycled water. It is important to emphasize the benefits of the recycled water. Recycled water can be specially beneficial for agricultural purposes because wastewater can be treated in a fit-for-purpose manner so that the nutrients can be retained in the recycled water. This will reduce the additional consumption of nutrients in farms. Recycled water will also allow the fresh water to stay in river systems, producing the required environmental flow to maintain the health of the river ecosystems. The Murray-Darling Basin is a great example where the rivers pass through 4 states and suffer due to the lack of environmental flow, algal bloom due to nutrients, as well as salinity and erosion. Further, recycled water from metropolitan wastewater treatment plants could be used to sustain agriculture in peri-urban areas. Transporting the agricultural products from peri-urban areas could become a lot easier. Another example on how the recycled water can be utilized in urban developments. Fishermans Bend in Melbourne is the largest urban renewal project that will be using rainwater and treated wastewater to reduce the freshwater consumption by 45% and halve the amount of wastewater discharged to the sewer system. Smart rainwater tanks and precinct-scale sewer mining plant are used for this purpose. Not only that, we also can treat grey water and black water generated from homes using very simple technologies to reuse the treated wastewater or to reduce the amount of nutrients and other pollutants entering the freshwater environments. Another example on reusing industrial wastewater. In this case, wastewater generated in car wash stations. In Australia, automated car wash uses 200 litre per wash. Manual wash requires 40 to 50 litre per wash. Thus, a car wash station could use 3.5 million litres of water every year. There are 10,000 car wash facilities in Australia using 35 billion litres of water every year. Purchasing this water and treating the wastewater generated will cost 77.35 million Australian dollars. By recycling the wastewater will not only reduce the freshwater consumption, but also prevent the wastewater entering sewer systems and obviously will have economic benefits due to near zero liquid discharge. We can extend this concept to many other industries such as mining, aquaculture, and textile mills. Membrane bioreactors and reverse osmosis systems can be applied to achieve zero liquid discharge, that is ZLD, in textile industry. Large-scale ZLD plants using activated sludge process, ultrafiltration, and reverse osmosis are being operated in India already. This is one of our lab-scale studies evaluating the performance of a MBR treating synthetic textile effluent. 2 anoxic bioreactors followed by a submerged aerobic membrane bioreactor and a UV disinfectant unit are employed to treat the wastewater. This is one of our pilot scale studies evaluating the performance of an MBR treating 10,000 liters of aquaculture effluent per day. One of our aims is to understand the issues faced in treating different types of industrial wastewaters. You would have noticed that I have included the issues when treating car wash water and textile wastewater in my previous slides. When treating aquaculture wastewater, we need to overcome the following issues. Low BOD in the aquaculture effluent causing low carbon to nitrogen ratio and reducing denitrification efficiency. Performance of microbes under different salinity, as the system could be switched from one salinity to another at different stages of production. Fouling of membrane. We have looked at how recycled water can be produced from different types of wastewater. Let us move on to stormwater. Flooding is becoming more frequent in many cities due to increased severe storm events and an increase in non-permeable surfaces. Stormwater overflow following heavy rainfall disperses waterborne contaminants with significant impacts on the health of our waterways and catchments. For example, stormwater carries 14,000 tons of sediment, 650 tons of nutrients such as nitrogen from fertilizers, litter, heavy metals, and bacteria into the Yarra River each year. Around 540 billion cubic meter of stormwater flows into Port Phillip Bay annually. Water-sensitive urban design, sponge city program, sustainable urban drainage systems, low-impact development, and stormwater harvesting are used to manage stormwater and mitigate flood. This is one of the ways to produce fit-for-purpose water from stormwater. We can capture the stormwater, treat, and then recharge into groundwater aquifer. The treatment can consist of UV irradiation for photolysis, iron filling and sand to remove phosphorus and metals, wood chips to remove nitrate, biochars to remove E. coli, and manganese to do further oxidation of remaining organic pollutants. Impaired water consisting of domestic wastewater and stormwater can be harvested for agricultural purposes. For example, impaired water can be treated by a membrane bioreactor, and the effluent from the membrane bioreactor can be the feed solution for a forward osmosis reactor, where concentrated fertilizer can be diluted for the application in agricultural fields. We are working on developing membranes and characterizing them and applying them in such processes, as well as modeling the fouling and their performances. This conceptual diagram shows how membrane processes such as membrane bioreactor, forward osmosis, and membrane distillation can be integrated to produce potable water and nutrient-rich effluent. Thermal energy for the feed of membrane distillation can be provided by a salt gradient solar pond, leading to the use of green energy. Multiple membrane barriers allow to produce high-quality potable water. Let us look at recovering other resources such as salts from desalination, minerals and water from mining, energy and value-added products from wastewater treatment, again, energy and value-added products from solid waste and landfill mining. Reverse osmosis, RO, is used to desalinate seawater and brackish water. Microfiltration, MF, and nanofiltration, NF, are used as pre-treatment to improve the performance of RO. Such system should be optimized to have high water recovery with low production cost. In order to do so, an additional process called membrane crystallization can be introduced. The last row of the table shows such a system, which will have 92.4% of water recovery and capable of producing 19.5 kilogram of salt per cubic meter of feed water. Thus, a RO desalination plant with 25,188 cubic meters per day of feed flow will run on profit due to the production of salts whose annual sales will exceed the annual operating costs. Reductions in operating costs are due to the use of energy recovery systems as well as the availability of waste thermal heat on site. This is a typical membrane crystallization system where a membrane distillation is coupled with a crystallizer to produce salt crystals. The concentrate from nanofiltration or RO will be fed into membrane distillation. The top table shows the water quality parameters of seawater, NF permeate and NF retentate. Retentate is called as concentrate. NF concentrate is treated first to remove the calcium ions present in it by precipitating them as calcium carbonate using sodium carbonate. The supernatant from the precipitator goes to a membrane crystallizer to produce sodium chloride and magnesium sulfate. 1 cubic meter per hour of NF retentate can produce 35.5 kilogram of sodium chloride, 8.4 kilogram of magnesium sulfate, and 2.9 kilogram per hour of calcium carbonate. We conducted a study in a zinc mine in Australia and developed a design to recover water and minerals such as manganese, zinc, and magnesium. A plant to treat 900 cubic meters per day of tailings wastewater will require $3.66 million to construct. The annual operating cost will be $1.52 million. Water savings and sales of minerals will yield $2.44 million. Thus, the payback period will be 4 years. Let us move on to energy capture from wastewater treatment. When a plant treating a wastewater stream, the COD of that stream will be distributed to the effluent, CO2 and methane produced, as well as the digested biomass. If we need to recover energy, we have to maximize the production of methane. In other words, high proportion of influent COD should be converted to methane. Every gram of COD can produce methane that can possess 5.98 kilojoules. How do we maximize the conversion of COD to methane? A wastewater treatment plant can have two stages, stage A to capture energy and stage B to remove nutrients. Part of the energy produced in stage A can be used to perform stage B. Remaining energy can be used for other purposes. Stage A could be a chemically enhanced primary treatment or a high-rate activated sludge process or an anaerobic process. Similarly, stage B could be shortcut nitrification and denitrification or partial nitrification and anamox. It has been found anaerobic process and partial nitrification and anamox can convert 73% of COD to biogas. Thus, selection of appropriate processes are essential to maximize methane production. In case if we wanted to use the nutrients present in the wastewater, An anaerobic MBR could be used to produce methane, and the nutrient-rich effluent can be used to irrigate agricultural lands or to recover nutrients. Significant amount of methane can be dissolved in the effluent, which too can be captured. Recovery of organic acids from the effluent is also possible. More than 20 milligram per liter of methane can be dissolved in water at 20 degrees Celsius. If the water has salinity, the dissolution of methane will be lesser. Letting this methane escape to the atmosphere is not desirable, as its global warming potential is 28 times more than that of carbon dioxide. We use liquid gas separation membranes to recover dissolved methane from an anaerobic membrane bioreactor. We use both dense and microporous hydrophobic membranes to conduct long-term experiments to evaluate fouling and pore wetting. We are also in the process of developing mathematical models to simulate the performance of those membranes. This is an excellent example showing how a food waste refinery model could help to produce various value-added products and energy. Biodiesel, alcohol, organic acids, and microbial oils can be produced through appropriate processes. Biogas produced can be used for energy generation. Carbon dioxide produced can be used for algal production, which in turn can produce microbial oil. The digestate can be used to produce biochar, heat and electricity, as well as fertilizers and soil conditioners. My colleagues at RMIT are in the process of constructing mobile biochar unit capable of utilizing various sources as feedstock. A PhD student is working under the supervision of RMIT, Indian Institute of Chemical Technology, and the State University of Maringa in Brazil. She is conducting research on extracting value-added products from food waste. This is the first part of her work, selective extraction of polar lipids from mango kernels using supercritical carbon dioxide. Every year, 30 to 50 million tons of mangoes are produced globally, 40% by India, with more than 30 varieties. 35 to 40% bio-wastes are produced when consuming mangoes. 20% of a mango is its kernel, which has 7 to 11% good quality fat, 95% non-polar lipids, and 3 to 4% polar lipids. This is a good substitute for cocoa butter. Extracting the fat using supercritical carbon dioxide will lead to cleaner production. Thus, the study was to find the optimum pressure, temperature, and CO2 flow rate through response surface method analysis. Optimum conditions were found to be 50 megapascal pressure, 40 degrees Celsius, and 28.3 gram per minute CO2 flow rate. Polar lipid yield was 3.38% with a phosphorus content of 88 milligram per kilogram. The study also proposes a full-scale plant design to process 3,000 tons of mango kernels per year. The plant is designed to operate continuously for 300 days per year. The payback period of the plant will be 5 years from the beginning of the construction of the plant. Since the carbon dioxide is reused in the plant, only 1,080 tons of carbon dioxide will be required annually. Thus, this will reduce the carbon dioxide emission by 106,000 tons per year. The second part of our study was to extract y-Oryzanol from defatted rice bran using supercritical carbon dioxide. India contributes to 20% of the global rice production and produces 100 million tons of milled rice every year. Rice bran is a byproduct of milled rice and contains several bioactive compounds. Y-Oryzanol is one of them, which prevents lipid oxidation and free radical-induced diseases such as cancer. It also reduces cholesterol levels in our bodies. Thus, it is a very valuable product for nutraceutical and pharmaceutical industries. Again, the optimum conditions for supercritical carbon dioxide extraction of y-Oryzanol were found to be 23.9 megapascal pressure, 48.9 degrees Celsius, and 29.8 gram per minute of carbon dioxide flow rate. Y-Oryzanol content was predicted to be 36,000 milligram per kilogram. A full-scale plant has been designed to produce 110,000 kilogram of y-Oryzanol per year, and the payback period is little over 5 years. It is important to quantify the contributions of resource recovery and concentrate management towards sustainable development goals. The processes shown in this diagram show how well we could contribute to sustainable development goals. We are collaborating with State University of Maringa in Brazil to conduct resource recovery from e-waste. We are looking into resource recovery from solid, liquid, and gaseous byproducts using membranes and supercritical oxidation technologies. The transition towards a resource-efficient, climate-neutral, and circular economy is one of the grand societal challenges of today, as endorsed by the European Commission in its European Green Deal. The Commission has launched a new circular economy action plan. Sustainable products policy that prioritizes reducing and reusing materials before actually recycling them, that is, moving up the waste hierarchy, will be proposed by the Commission. However, it does not yet address the question of what Europe and other countries in the world will do with the vast amounts of industrial and consumer waste that have been disposed of in waste dumps and landfills over the past 100 years. In this context, enhanced landfill mining, ELFM, has been proposed as an out-of-the-box approach to address the dark side of the circular economy vision. That is, how can we deal with the waste of the past? Enhanced landfill mining, ELFM, is considered as safe conditioning, excavation, and integrated valorization of landfilled waste streams as materials and energy using innovative transformation technologies. ELFM will be respecting the most stringent social and ecological criteria. Therefore, ELFM can be considered as resource recovery and remediation strategy. It reclaims valuable land and also it unlocks valuable resources. Sustainable future depends on many things. One of them is how we are going to use the available natural resources. We touched upon how valuable and limited the fresh water is. How can we manage the fresh water sustainably? Integrated water management is the key. We should produce fit-for-purpose water and recycle treated wastewater at individual households, precincts, and industries. We should encourage zero liquid discharge when appropriate. We should capture, treat, and use or store stormwater. For all the above, we should employ appropriate technologies. We should advance them while finding techniques to reduce their energy consumptions. We should look for issues to be solved which can lead to more resource recovery. For example, salt recovery in desalination and mineral recovery from mine waste are achievable even at large scales if we continue to improve our technologies. Energy efficiency is very important. Industries are working on zero emissions from their operations. Water industry should select processes to recover energy and nutrients. Food waste refinery model teaches us that resource and energy recovery is achievable from food waste. We need to expand this kind of approach everywhere for a sustainable future. While we master our technological skills, we should not forget the human basics. Following the nature can still teach us many things to live happy and healthy. Thinking outside the box to arrive at great solutions. Having good habits, example, using water and energy carefully, not letting the tap run while brushing, switching off electrical appliances when not in use. International cooperation for shared destiny of mankind. Devotion and passion for our work and respect during our day-to-day dealings with others. Continuous learning of anything and everything. I take this opportunity to inform you that I am the editor-in-chief of the journal Environmental Quality Management by Wiley Publisher. The themes of the journal are resource recovery, concentrate management, waste management and conversion, research translation and impact, cleanup production, and emerging sustainable practices. You are welcome to submit your manuscripts to this journal. I am also the editor-in-chief of a book series on applied environmental science and engineering for a sustainable future by Springer Publisher. We look for book proposals on solutions to environmental problems related to air, water, and soil. So far, 12 books have been published under this book series. Please feel free to contact me if you plan to write a book relevant to the scopes of the series. Once again, thank you very much for listening, and I'm happy to take any questions.
Okay, thank you very much, Jega, for the very enlightening presentation. I got some feed from the FB page saying that your sharing also served as their enlightening. Some of them has left the university for quite some time now, serving at the industry and everywhere else. So they're saying that this serves as a very good lecture for them to revise back what they have learned in the university days. Okay, Jega, I think while waiting for the secretariat to share some questions, yeah, they will share and it can appear at the your screen.
Okay.
So yeah, can you see the question, Jega?
So far, no.
Okay, I think are you opening any PowerPoint in your desktop now?
Okay. I am seeing the comments. Yeah.
Yeah,
I
yeah. Okay, this is actually a question by I think one of our students,
Right.
Tan Ai Yi.
Yeah.
So he is asking, is distillation a sustainable way of generating fresh water?
Yeah. I think that's a very good question. Normally, distillation will become very efficient if we have waste heat. So when you have a desalination plant, you are operating pumps and various things. There you will have ample waste heat. So that waste heat can be used to heat your feed stream to the membrane distillation. Then you can produce. So, but a lot of research is going on to improve the membrane performance and low thermal, even at low temperatures, around 30-40 degrees. If the feed stream has, still it can produce good amount of water. So it is energy intensive, but you have to get the energy from uh, like a cheap sources, and also from solar energy. So another thing I showed you, we can have like a salt gradient solar pond. Those solar ponds can store the heat up to even 90 degrees it can store. So at the bottom of the solar pond, your temperature will be 90 degrees. So that water can be used to heat your feed stream for a membrane distillation. So that's how you utilize membrane distillation.
Okay, Jega, thank you very much for the answer. I hope it answers Tan Ai Yi's question. So While waiting for the question, Jega, maybe I can would like to ask your opinion on something. You mentioned about having a mobile treatment unit.
Right.
Okay, in RMIT already have a mobile treatment unit where you targeting to produce at the end of the day biochar.
Yes, correct.
So
So
yeah, please, Jega.
go ahead. You are asking some more.
I mean, like in terms of the feasibility, I mean that in terms of the supply of the raw materials, is it oh was I mean like is it okay for us to also look into this possibility?
Yeah, definitely. Because sometime that you can see that if you install in one place, whether will you get a continuous supply of raw materials for that one. So that if that is not possible, you move your plant to different places will become useful. So that should be actually a strategic thinking. Which one will be really useful? For in our case, it's possibly in a urbanized area, maybe it is kind of useful to go to some place, um, utilize them and produce some biochar and come back. So it is a strategic decision you have to make. um, but in one place, if you are going to get continuously the raw material for biochar production, then you can do that one. Mostly if you target a wastewater treatment plant, the amount of biochar may be the waste generated may be not that much. So depending on the size of your wastewater treatment plant, in that case you can different places, so that will become beneficial.
Sure.
Yeah, and I can get some more example by talking to my colleagues to see what are the other things in their mind that led them to go for this um, uh, mobile biochar unit.
Yeah, why the question, Jega? Because sometime when we had the chance to discuss with the industry people, some of them is quite reluctant to put in high initial cost, capital cost. Yeah.
Hmm.
So
That is
this is actually one of the very good alternatives to them, for
right.
them, for them and us to collaborate and to work together to manage their waste generated and to be converted into something valuable and useful with not that much of a cost that they need to invest. So MTU is a very good alternative, Jaga.
Yeah, yeah. That is true. And yeah, obviously, like you said, that you don't need to install many things in different places. Rather, you use one to work around. So, in a way, your capital investment also will be reduced significantly.
Yeah.
Yeah.
Okay, Jaga. Maybe another questions from me.
Mhm.
You mentioned that one of the industry that you are working is you handle their waste is a mining industry. Yeah.
Correct.
And also other industries, but we also know that this industry are normally situated far from the residential area. Okay, so if we are going to propose to the industry that by having a water recycling facilities where they can reuse the recycled water and sell it later, so who are the main beneficiaries of the recycled water, because the residential area is quite far away?
Yeah, that's a good question. Most of the time, the industry need certain amount of water, right, for their purposes. For example, the mine, you can see they use 900 cubic meters of water, right? So if you are treating that water and you are giving that back to them, then they are not going to tap the fresh water anymore. Or maybe they will reduce the amount of fresh water they are getting from the main supply. So our first target is to uh, maximize their usage of recycled water. So within the industry, we try to make them use, because they take certain amount of water, they release it. What we are doing is, don't release that one. You treat as much as possible and you reuse it. So you keep reusing it. So that
Yeah,
is our main idea, because that will be the industry purposes. They will take water for their need and they will try to release it. we are stopping that one. But if you go to the domestic wastewater side, yeah, obviously large amount of water will be used, and when you treat, you may not be able to reuse everything. That is the issue. So in the industry, we can make them use their treated wastewater within the industry, but when it comes to domestic one, we fail. In Victoria, we wanted 30% of the treated wastewater to be reused in the community, but we are using only 7%. That is because it is very hard to encourage them to reuse. So that
Yeah.
is where more policies should come, kind of more educational awareness should come, so that people will start to use it. Most of the time, people are willing to use when we give the proper information. So proper education, clear instructions. Obviously, you have the example in uh, your neighbor country, Singapore, how much they encourage the people, and how much people are accepting the recycling water. So that is the kind of things we are lacking currently. And the policies are very important. That's what we are seeing, because um, sometimes we cannot force the people to use it, but if we can kind of give a good education, people will start to use.
Yeah,
I hope
Jega.
I answer your question.
Yes, Jega. That was a very good input from you, because if I may share, I think the same situation we are facing also in Malaysia. Yeah,
Mm,
because sometimes when we try to discuss with the industry to reuse back their water, especially not from the agriculture section, they will say that the cost of the to build the container, right? Because
mm,
to recycle back the water, they need to contain the water first. So the
mm,
cost of building that would normally would be very high. In the end, they choose not to. They choose to just use the water supplied from the JBA here,
mm,
the water supply company. So I know, and also you mentioned about the policy legislation is also same here in Malaysia. How the industry who are involved in this kind of activities, namely they will give given uh, like a bonus or an opportunity to apply for a green company status,
right,
yeah, or a zero waste discharging company status, which comes with it a lot of benefits. Yeah,
right.
I think similar things are being applied also in Malaysia. So I think, Jaga, it's nice to know that both our the place that we're living now, Malaysia and Australia, both are heavily promoting about this
Yeah,
recycling and to safeguarding our source of water.
yeah,
Okay,
yeah. And
we'll take, yeah.
And a very good example in India, in Tamil Nadu, there are a lot of textile industries there. They have a central treatment plant. They actually large amount of water, like sometime 10,000 to several 100,000 cubic meters of water from the textile industry treated and reused. We visited there. So almost 99%, more than 90% reused. And also they produce salt. The salt also go as a solution back to the industry.
Mm,
So that is like a near zero liquid discharge.
wow.
So their aim now is to improve. They use the activated sludge process for treatment, then go to the membrane processes. They are trying to see whether we can improve the processes to reduce the cost. So, so the next step, they are trying to reduce the cost. So already the technologies are there. So we actually have to focus on that one. Our aim should be to inform the people we better don't pollute the existing fresh water. Like for example, if we get some water, can we keep using it as much as possible so that we don't touch the existing other fresh water? That is
Yeah.
the message should go to everybody.
Yes.
That doesn't go. Sometimes it looks like we have a lot of water here, so people don't mind. But as I mentioned, somehow we are polluting them. They are not any more fresh, right? Because some pollutants are there. Any
Yeah.
water, you can see some BOD there, COD there. Maybe
Yeah.
if you go back few hundred years ago, there won't be like that. You wouldn't have seen many different pollutants in the water. So we already impaired the water already. So doing that, the concentrations will slowly increase in everywhere. Maybe not our generation, even another 5-6 generation, but it can happen.
Sure, Jega.
Yeah.
It is our role, especially the lecturers at the university and all the educators out there, to always educate, especially the school children, the university students, about the importance of all this. Yeah, Jega. So for the secretary, do we have any more questions from our audience at our FB page? Okay, so Jega, in your presentation also, you mentioned about one of the main cause of water not being able to be fully transported to destination is non-permeable surfaces.
Right.
Yeah, it causes flooding. Yeah, flooding which can cause the dissipation of essential nutrients for the plant to grow. Yeah. So I think we also encounter some area like that also in Malaysia, especially the dry area. Yeah. So any suggestion that you think that we can do? Maybe we can build some channel, maybe a canal, maybe, or what? Yeah, to channel the water.
Yeah. The non-permeable areas I am mentioning mostly in the urbanized areas, right? Because we have a lot of developments, so we paved the area, we block the water going into the groundwater. So then that start to generate the stormwater. Like you said, so the developments are already there. So what we are doing here, Zainul, we try to see whether we can have some nature-based systems like wetlands, swales, and like a rain gardens. So allowing the water to go through, so that slowly the pollutants are uptaken, the sediments are dropped in the settling basins, and so on. So that is the kind of best way in urbanized area to improve the quality of water that is going to enter a river, then further down it is going to the sea or whatever. So we actually involved in a big proposal recently with Europe, around 10 like industry partners, like a Suez, a big company. So what we are giving is, we are going to look into the nature-based systems in different countries, like Denmark, France, even a country in Africa, and several countries in Asia. How are they working? So that they can give urbanized areas. For example, if you have a good system, you can use them for irrigation, and you can reduce the heat, the urban heat island. The heat you can reduce in an urban area if you have this kind of nature. You can have vertical gardens, so that also can cool down the environment. So many things we can do by creating this kind of thing. That is one of the area we can talk about. Even in Malaysia, we can think how we can do this kind of activities, making the urbanized areas more livable through this kind of introducing nature-based systems, like a floating wetlands. I'm sure you must be doing something there, but there are a lot of things lacking in that area. Who is managing that one? How it is maintained? Whether in the long run they are performing what they have to perform? All kind of issues are there. So we are slowly building some understanding. So if we get that proposal, we are very excited to get the results in the near future, to see how we can go about it.
Yeah, Jega. Thank you very much for the feed. And I'm very sure also between our institution, we can also move forward with that kind of collaborations. So maybe because in UTM now, we have a lot of dedicated centers, and sustainable issues is a big focus of the university now. And also this is in line with the government agenda, yeah, to preserve our water sources, water resources, yeah. So, for example, we have the Advanced Membrane Technology Center in UTM. I
Right.
think you know about Professor
Yeah,
Fauzi.
yeah,
No?
I know
Right.
him very well. Yeah,
Yeah. And also we have the Dedicated Center of Water. You remember Professor Zainura last time?
yeah, yeah,
Yeah, she's in that
yeah.
center.
Right.
So, and also we have a lot of smaller research groups who are working definitely like the topic that you are discussing. So actually, we are really looking forward to have more collaborations with RMIT Jega in this kind of
Yeah,
area.
definitely. I think, yeah, we can do a lot of things. Yeah.
Yeah. So I think if there's no more question from the audience from our FB page, maybe again on behalf of all the audience and myself, I would like to thank you for your presence today. And with that, I would like to invite again our distinguished Dean, Professor Datuk Rafiq, to make the concluding statement. Over to you, bro.
Thank you, Zainul, for moderating the session and for introducing Professor Jega Jegatheesan to me. And to our distinguished speaker today, thank you so very much for a great sharing session. The topic is extremely important and it is very close to UTM because we have, as Dr. Zainul mentioned just now, we have several centers, research groups, tackling the issues of water and sustainability. So it is an interesting topic, and thank you again for a great sharing session. And to all our viewers worldwide, thank you for watching UTM Engineering Distinguished Lecture Series. Do stay tuned because we have many more interesting lectures for you. So until next time, bye-bye for now. Bye-bye and Assalamualaikum.
Thank you for the opportunity and have a nice day.
Thank
Thank you.
you. Thanks, bro.